Imagine a cosmic mystery unfolding billions of years ago, where a long-vanished planet collided with our young Earth to birth the moon. Now, groundbreaking research reveals that this enigmatic world may have started its journey much closer to the sun than we ever imagined. Buckle up, because this revelation could rewrite our understanding of the solar system's turbulent beginnings. Scientists have uncovered compelling evidence that Theia, the ancient planet thought to have played a pivotal role in forming the moon, likely emerged from the inner reaches of our solar system. For generations, the dominant narrative has been the giant impact theory. Around 4.5 billion years ago, a massive collision between Theia and the early Earth sent debris flying, which eventually coalesced into our lunar companion. Picture it like a colossal cosmic car crash, where materials from both bodies mix together to create the moon we know today. This theory gained traction after the Apollo missions brought back moon rocks over 5 decades ago, offering the first real clues. But here's where it gets controversial. Despite all this, Theia itself vanished eons ago, leaving no direct traces, no fossilized fingerprints to confirm its story. Its origins and makeup have been shrouded in uncertainty, making it one of the biggest puzzles in planetary science. Could this mean our textbooks need a major update on how celestial bodies form and collide? Enter a collaborative team of astronomers from France, Germany, and the United States who dove into ancient rocks from Earth and lunar samples retrieved by Apollo astronauts. Their goal? To trace Theia's roots through isotopic analysis. Think of isotopes as unique chemical markers, variations in elements like iron, chromium, zirconium, and molybdenum that act like DNA for planets, revealing their formation environments. For beginners, isotopes are like flavors of the same element. They differ based on where and how they were created, influenced by factors like temperature and proximity to the sun. Scientists knew Earth and moon rocks shared nearly identical isotope ratios, which blurred the lines between what came from our planet and what from Theia. But in a clever twist of planetary detective work, the researchers employed a technique akin to reverse engineering a machine. They modeled countless scenarios for the early Earth and Theia, tweaking variables to match the isotope signatures we see today. By doing so, they discovered that Theia's isotopic fingerprint points to an origin in the inner solar system, possibly even nearer to the sun than Earth's original position. This flies in the face of some old ideas that placed Theia farther out in the colder outer regions. And this is the part most people miss. The excitement isn't just in solving a riddle from the past. It's in how precise this method is. As Jake Foster, an astronomer at the Royal Observatory Greenwich in the UK, who wasn't part of the study, puts it, one of the things about this research that does make it so exciting is not only is it helping to paint a picture of what happened to the Earth 4.5 billion years ago, but also it's able to almost exactly pinpoint where this object came from. He adds, "We're talking about a planet that doesn't exist anymore. It was completely vaporized essentially, and yet with a good amount of precision, we can figure out where it came from. It's like piecing together a shattered vase from just a few shards. Astonishingly detailed for something so ancient. This breakthrough isn't just cool trivia. It could inspire future studies on planetary growth, collisions, and evolution in fledgling solar systems. For instance, understanding how inner solar system conditions shaped Theia might explain why our moon has such a unique composition compared to other moons in the galaxy. As an example, think about how Earth's proximity to the sun led to faster material processing, which might have given Theia distinct traits that influenced the moon's formation. But let's stir the pot a bit, Does this inner solar system origin challenge the notion that giant impacts were random? Or could it suggest a more structured dance of planets in the early days? Some might argue this reshuffles our view of planetary migration, potentially sparking debates on whether such collisions were guided by unseen forces or pure chaos. What do you think? Does this make the solar system feel more predictable or even more mysterious? Share your thoughts in the comments below. Do you agree this could revolutionize astronomy, or disagree that it's just another layer to an already complex puzzle?